During this segment, we will be simplifying radical expressions. We need some tools to help us simplify radical expressions. The first tool we'll use is the product rule. Let's review that rule. This is the product rule for radicals. If the nth root of a and the nth root of b are real numbers, then their product, the nth root of a times the nth root of b, is equal to the nth root of a times b. So in general, we have the following. In this case, the square root of 2 times the square root of 3x. Notice this index is the same as this index, so by the product rule, I can write this as the square root of 2 times 3x, and of course I can simplify a little. 2 times 3x, that is 6x. So there's an example of using the product rule. Let's now review another tool we'll use, the quotient rule. This is the quotient rule for radicals. If the nth root of a and the nth root of b are real numbers and the nth root of b is not 0, then the nth root of the quotient, a over b, is equal to the nth root of a over the nth root of b. Now, if you notice, we will use that quotient rule, reading it from left to right and from right to left. You'll see as we use the quotient rule both ways. Here I'd like to simplify the square root of 6 over 49. Well, by the quotient rule, I can write this as the square root of 6 over the square root of 49. Now, how does that help me? It helps me because I know 49 is a perfect square, whereas 6 is not. So I can at least evaluate the denominator. In the numerator, I have the square root of 6. In the denominator, the square root of 49 is 7. Now, by the way, can I simplify at all in the numerator? The answer is no, because 6 contains no perfect square factors. Here I've simplified, and there's my result. Let's continue using, though, this quotient rule. Let's suppose I have, say, the fourth root of x cubed over 16. I'll use the quotient rule to help me simplify this. I'll make this the fourth root of x cubed over the fourth root of 16. How does that help? Because I can't evaluate the fourth root of 16. The fourth root of 16 is 2. And I can also work on these radicals separately now. What about the numerator? Can I simplify that? Well, remember this shortcut, if you have an exponent, will 4 divide into 3 a whole number of times? The answer is no, so there's no simplifying that can be done in the numerator, and we just leave that as the fourth root of x cubed. So I hope you see how that quotient rule helped us do some simplifying here. Let's continue simplifying. Let's simplify this expression. Now, by the way, notice this radicand. There is no simplifying that can be done within the radical sign. Were there, I would certainly do it. But no simplifying there, so I'm going to separate the numerator and the denominator. The reason being that I notice the radicand in the denominator now is a perfect square. So let's go ahead and simplify that part, the denominator. The square root of 4 is 2. And then what about the square root of y squared? Remember, the index is 2. 2 divides into 2 one time. So that's y to the 1, or simply y. Now, in the numerator, I have the square root of 5x squared, which I can look at separately as the square root of 5 times the square root of x squared, actually using the product rule. The square root of 5 cannot be simplified, but the square root of x squared can. The square root of x squared is x. And then I have square root of 5 over 2y. I've simplified as much as I can. Let's continue. We're going to use the quotient rule a little differently now. Suppose I have, say, the square root of 14 over the square root of 7. Separate square roots this time. Well, notice 14 and 7, obviously there's a common factor of 7 there. So I can do that if I use the quotient rule and write it as the square root of 14 over 7. I saw some simplifying that could be done, but I have to use that rule and write numerator and denominator under the same radical sign. So now this is the square root of 2, because 14 divided by 7 is 2, and then 2 contains no perfect square factors, so I am simplified. Let's try that one more time. We're still using the quotient rule, but just in a different manner. Suppose we have the square root of x to the 5th y cubed over the square root of xy. This time separate square roots already, but I notice that there is some simplifying that can be done if I write the numerator and denominator under one radical sign. I can do that because these are both square roots and because of the quotient rule. X to the 5th y cubed over xy. Now let's just concentrate on within the radical. X to the 5th divided by x, that's x to the power of 5 minus 1 or 4. And y cubed over y, that's y to the power of 3 minus 1 or 2. And now let's simplify if we can. Remember, the index is an understood 2. 2 divides into 4 2 times, so I have x squared. And here 2 divides into 2 once, so I have y. This simplifies to x squared y. Now let's look in general when we have simplified an expression. In general, we say that a radicand of the form nth root of a is simplified when the radicand a contains no factors that are perfect nth powers other than 1 or negative 1. So you'll see what we mean as we look at the square root of 32. We don't want to approximate it, we just want to simplify if possible. So let's ask ourselves the question, does 32 contain any perfect square factors? Well, 32 has a factor 4, and 4 is a perfect square, but 32 contains an even larger perfect square of 16. So we can write the square root of 32 as the square root of 16 times 2, and then by the product rule, this is equal to the square root of 16 times the square root of 2. Then we can evaluate the square root of 16 as 4. So I have 4 times the square root of 2, or we write simply 4 square root of 2. Now, by the way, had you used the perfect square factor of 4, you would have just simplified this twice, because you always still need to see if the radicand contains any perfect square factors. Well, notice this radicand of 2 now contains no more perfect square factors other than 1. Now let's continue on. We are simplifying radicands. Suppose I have the radicand, the square root of 25 a squared b cubed. We can take each of these factors separately because of the product rule. And if you'd like, we can go ahead and work on them together. I know the square root of 25 is 5. Now these are exponents. Think of the index of 2. 2 divides into 2 one time, so I know a factor of a to the 1 I can take outside the radical. Now what about b cubed? 2 divides into 3 one time, but there's a remainder of 1. Whatever the remainder is, that's how many factors, or that's the exponent on this variable that must remain within the radicand sign. So here we have 2 divides into 3 one time, but I have a remainder of 1, which means there is a factor of b, or a factor of b that stays within the radical. There we have simplified. No more perfect square factors. I'm simplified. Let's try this again. What about the fifth root of negative 32 x to the 10th y? I'd like to simplify this radical. Well, to do so, we are really using the product rule. It's the fifth root of this factor times the fifth root of this factor times the fifth root of this factor. But let's see if we can't work it all mentally. The fifth root of negative 32, that is negative 2, because 32 is a perfect fifth power. So the fifth root of negative 32 is negative 2. Now here we're working with exponents. Does 5 divide into 10? The answer is yes. It divides 2 times with a remainder of 0. So that means x squared outside the radical and no factors of x underneath or within the radical. Now what about y to the 1? 5 divides into 1 0 times with a remainder of 1. So that factor of y to the 1, or just y, remains under the radical. Be real careful when using that shortcut with the index and exponents. But I've simplified that expression. Now let's look at an application of working with radicals. One application is the distance formula. Let's look at the distance formula. The distance d between 2 points x sub 1 y sub 1 and x sub 2 y sub 2 is given by d is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1, that quantity squared. Let's now find the distance between these 2 points. So we will use the distance formula. The distance is equal to the square root of, it's the difference in the x values squared. So I'll start, say, with this x value. 1 minus, be very careful then, a negative 3 squared plus the difference in the y values squared. Here's this y value, negative 3, minus this y value of 2, and then once again, squared. Now we just need to evaluate this expression on the right. So let's see what we have. We have the square root of 1 minus a negative 3, that's 1 plus 3, and 1 plus 3 is 4, so I have 4 squared plus, and then that's negative 5 quantity squared. So it's the square root of 4 squared is 16 plus negative 5 quantity squared, that's 25. And what is 16 plus 25? That is 6 and 5 is 11. Carry the 1, that is 41. Now can I simplify? The answer is no, because 41 contains no perfect square factors other than 1 here. By the way, you can go ahead and approximate this, but right now we'll just leave it as an exact value. Between these 2 points, the distance is exactly the square root of 41 units, and you know that this number is between 6 and 7, because 41 is between 36, whose square root is 6, and 49, whose square root is 7. Now let's look at another formula. Here is the midpoint formula. Now keep in mind that the midpoint is a point. The midpoint of the line segment whose endpoints are x sub 1, y sub 1, and x sub 2, y sub 2 is the point with coordinates. X coordinate is, notice it's the average of the x values, x sub 1 plus x sub 2 all over 2, and notice the y coordinate is the average of the y values, y sub 1 plus y sub 2 all over 2. So let's find the midpoint of the line segment with these points as endpoints. And that midpoint then is the x value, just think average, is the average of the x values. And to find average, you add, so this x value plus this x value over 2, and then let's take the average of the y values. That y value plus that y value all over 2. We need to simplify, but that is the midpoint. Let's simplify. Negative 2 plus negative 8, that's negative 10, divided by 2, that's negative 5. And then negative 1 plus 6, that's 5, and so I have 5 over 2, or you can write this as, of course, 2 and 1/2. Now, by the way, how can you check? You might want to go ahead and plot these 2 points and then plot this one and see if it at least looks like it's between these 2 points. That's one good way to at least see if your answer is reasonable. All right, at this time, practice simplifying radicals.